So asymptotes are essential when it comes to rational functions because they actually help guide us into figuring out what the properties of certain asymptote, or I should say certain rational functions. And so when we think about asymptotes, well, they help with, first and foremost, the domain, right? And this is going to be guided by the vertical asymptote. I'm going to write asymptotes with the S in brackets here because sometimes you can have more than one. The range is guided by the horizontal asymptote. So it kind of provides a min and a max. And then the end behaviors, well, really your graphs, and I'm just going to write here, graphs follow the vertical and horizontal asymptotes. So once you draw in your asymptotes, then your graphs are going to follow that both vertically and horizontally. So it all really stems from the asymptotes. So let's say I have my rational function graphed here, which is 4x minus 5 over x minus 2. And this is the graph over here. So what we're going to do is, because I want to figure out, let's say, the domain and range, I'm going to write it over here. So I want to know what the domain is, what the range is, okay, and then any intercepts. So I'll just write x/y intercepts. I'm going to need to get my asymptotes. So let's do all the work we did in the previous questions and get the asymptotes, and we'll see why that works. Now I'm going to key them in. And we're going to see that they act like guiding lines. So I've drawn my asymptotes here in green and I point to which one is which. And so what we're going to see is the following. If I'm looking at the domain, well, I see that x, and I'll write it in black here, that x cannot equal 2. And then if I'm looking at the range, I know that y cannot equal 4. Okay, so now x could be infinitely smaller than 2, right? Or it could be infinitely greater than 2, but it cannot be 2. And same with the range. Now for the intercepts, x and y intercept, there's an x-intercept over here, which we could say is about, if I look at my graph here, so there's an x-intercept of about, we'll just write x equals about 5 over 4. And then the y-intercept is going to be at about 5 over 2, so y equals 5 over 2. And when we said end behaviors and how they follow the lines, well, because if we start at the y-intercept here, I can see that my graph follows the horizontal line from here, the horizontal asymptote at y equals 4. And it also follows the vertical asymptote at y equals 2 going this way. Same with any point here, right? It's going to follow along the vertical asymptote at x equals 2, so it'll approach it but never actually hit it. Over here at the top, it gets really close, but you see that it never actually hits. And then at the same understanding, it's going to approach the y is equal to 4 horizontal asymptote, but it never actually hits. There's always a small line. So you really guide the end behaviors of the graph once you plot all your points. So let's say we take a reciprocal function, f at x is equal to 1 over x, and we're asked for the domain and the range. Again, what we need is the vertical asymptotes. So if we think about, for the vertical asymptote, the value of x that is going to make the denominator 0 is going to be 0. So we're going to write x is equal to 0. For the horizontal asymptote, if the degree of the numerator is greater, or I should say less than, the degree of the denominator, then it has a horizontal asymptote at y equals 0. This, here the 1 has a degree of 0, since there is no variable, and this has a degree of 1. Therefore, it does fall into the category where the numerator is less than the denominator. So that means it'll have an asymptote at, or horizontal asymptote of y equals 0. Now when we camera it in here, we see that the values approach 0, both horizontally and vertically, but never actually hit it. They almost go side by side, but this has to do with the thickness of the red line and not the fact that they actually make contact with the asymptotes. Now, if we're writing the domain using X builder notation, we could say that X, all numbers included in the data set of X such that X is all equal to real numbers, where X cannot equal 0. And this is set builder notation. We can also say the same for the range, where all values of Y such that Y is all real numbers and Y cannot equal 0. Now, if we wanted to write it in interval notation, we could write it as follows. We could say that, and we'll use round brackets, that as x goes to negative infinity, so round brackets negative infinity to 0. Now 0 is not an included point because it is an asymptote, so we include round brackets, and or unified by the same function. So this section of the domain describes this portion here. But if we're going to describe this portion of the graph over here, but it's the same function, we write union, and then of course not including the 0. So we're going to use round brackets, and then x approaches infinity towards the right, positive infinity. And the same can be said for the range, right? Not put y, but we can just write r, whereby r goes to negative infinity if we're talking about this section of the graph. So from negative infinity to approaching 0, where 0 is not included, and or unified by the top portion of the function, the second curve, whereby you can say that as, or from 0, your y values approach positive infinity.